In this unit, we're going to start our examination of slightly more advanced concurrency APIs. What we have seen so far are what I refer to as the classic concurrency APIs. These have been in Java for a very, very long time. The things that we're going to cover from now on are some newer, I would say quote-unquote newer APIs, at least relatively. These have been in Java from Java 5 onwards. Some other APIs that we're going to talk about are even newer. But these APIs provide some higher level primitives for you to work with concurrency, and threads and the ability to start individual threads by giving it a runnable. This seems a little low level when compared to what I'm going to show you next. But however, in contrast to what I just said, there is one API which we're going to start our discussion with, which is the newer API, which is a natural extension of what we've seen for synchronized, and this enables unstructured locking. If you remember, we talked about the synchronized keyword being a structured locking mechanism. All right, why is synchronized a structured locking mechanism? This is because the lock and unlock is handled for you. It is implicit, right? Acquiring a lock and releasing a lock is implicit. You don't have to do it. And you can also do nesting with synchronized keyword. You can have a synchronized block, and inside that you can have another synchronized block, which is synchronized on the same object or perhaps a different object. So for example, you do something like this, right? So synchronized with object 1, this gets executed only when the lock for object 1 is accessed, right, and acquired. And then when it comes over here, this gets executed only when this currently running thread has acquired the lock for both object 1 and object 2. So this is perfectly fine. Structured locking is great, but sometimes this kind of nesting might not work. So I'm going to give you a use case where nesting like this might not work, but there are lots of use cases where you would want to have more control. You want to have imperative control over when you acquire a lock and when you release a lock. Let me give you an example. Let's say I have an array, and I have to process this array, and processing basically involves processing a single element and then the next element together. Maybe I'm comparing two elements together or something like that. And what I'm doing is I'm just looping through I equals 0, I less than array size minus 2, I plus plus. I'm processing array of I and array of I plus 1. Okay, so two elements at a time. Now let's say I want to lock it. I want to make sure that this doesn't have concurrency issues. So what I need to do is I need to acquire a lock for both array of I and array of I plus 1. I don't want any other thread to work on array of I. I don't want any other thread to work on array of I plus 1 when this process is running. Okay, I know we can do nested locks. So what I'm going to do is I'm going to put a synchronized over here for array of I, and I'm going to put another synchronized for array of I plus 1. And within this inner block, I'm going to run process of array of I and array of I plus 1. So when something executes this, when a thread has to execute this, it has to acquire a lock for both the first element and the second element that I'm processing. Okay, this works fine, but you notice a problem here. I am kind of iteratively doing this, right? So I'm saying, okay, let's say an array of 10 elements. I'm going to get the lock for array of 0 and array of 1. Okay, I'm going to process this, and in the end, I'm going to release the lock for both array of 0 and array of 1. Okay, and the next iteration, I'm going to get a lock for array of 1 and array of 2. Okay, process, again, release both the locks. You see how this can be a little counterintuitive, right? It's doing more work than it should. So when I do the first pass, I have a lock for array of 0 and array of 1. Now, for the second pass, what I actually need to do is just release array of 0's lock, still hold on to array of 1's lock, and then acquire the lock for the next element. I don't have to release both the locks, only to acquire the second lock all over again for the next iteration, right? So this kind of approach is what's referred to as hand-over-hand locking. Okay, it's kind of like if you're imagine yourself using a rope to climb up or to get down. What do? You don't hold the rope with both hands and then release both hands and then hold the rope with both hands again. What you do, you release one hand, move your hand to the next thing, release your other hand, move your hand, and then that's how you climb a rope or get down from a rope. This is called hand-over-hand locking. You first get the lock for the first element and the second element in the array. Once you've done processing them both, release the lock for the first element and get the lock for the third element while still holding on to the lock for the second element, right? That's how you do this. So for this, the synchronized block will not work because you have to have those blocks be nested. So the way to solve this problem is by acquiring and releasing locks yourself. And Java has the ability for you to do that by using the lock interface. So here is the Java doc for the lock interface. So lock implementations provide more extensive locking operations than can be obtained using the synchronized methods and statements. They allow more flexible structuring for sure, and they have other properties as well, but you have the ability to do a dot lock and dot unlock so that you can control when the lock happens and when the lock is released. So I'm going to demonstrate this in IntelliJ, this synchronized program, which is basically this counter, which has three methods: increment, decrement, and get value. And what I'm doing here is I'm doing a run, and I'm synchronizing the call to increment and a call to decrement using this keyword. Now I'm going to update this to manually get a lock and release a lock so that I don't use the synchronized keyword for this. What I need to do here is to get a lock, acquire a lock over here, and what I need to do here is release the lock. Okay, this is what I need to do. I need to do this manually. I'm going to use the right term for this. It's acquire a lock and release a lock. Now how do I do this? So the first thing I need to do is create a lock variable. I'm going to create a lock variable here as a member variable of this class. I'm going to say private lock L equals, I'm going to create a new, I can pick implementation of this lock. So there are a bunch of implementations here. You see here, I'm going to pick the first one, which is the reentrant lock. Reentrant lock is a direct equivalent of a synchronized lock. Okay, so what does reentrant lock do? It basically says once you have acquired a lock in one place, you can acquire a lock again and again. You don't have to worry about it. Okay, that's what reentrant locks do. So I'm going to import this from concurrent blocks.lock. Okay, and both of these are from java.util.concurrent. Okay, this is the new package that was introduced in Java 5 to support some of these new APIs. So what I've defined here is a lock, which is a reentrant lock. Again, reentrant lock is very similar to what you've seen with the synchronized keyword. So here, what do? I first acquire a lock. Okay, so what I do is l.lock. This is it. I have acquired a lock. Okay, now this lock does not depend on another reference. It is not dependent on this keyword. This is basically a new lock that you have created. Okay, so this is not like, okay, give it any arbitrary reference and then there is a lock created for you for that. No, this is where you are creating your own lock, and this is exactly what that lock object is. There's no other object which from which a lock is inferred. Okay, so this is a lock and I have locked it, and over here I need to do l.unlock. So what I'm doing over here is I'm making sure that any thread that runs this method, it first has to acquire a lock on this lock object. And how many lock objects do we have? We just have one, because we just have one counter instance. Okay, so it's going to acquire a lock on this thing, and then it is going to execute this, and then it is going to release. Okay, the pattern that's typically used is not to just do an unlock over here like this, because you want to make sure that an unlock happens no matter what. Okay, for example, let's say this were to throw an exception. Well, then you have a problem, because the l.unlock is never going to get released. The synchronized keyword handles it for you, right? If the synchronized block throws an exception, the JVM takes care of releasing the lock. But here, now you're on your own. So what is typically recommended is to surround this with a try block. Okay, put this thing, whatever you need to run inside the lock, put this over here, and then have a finally block over here and release the lock only inside the finally block, so that you can be guaranteed that no matter what happens during the execution, the lock is going to get released. You can say, well, I'm confident that there's not going to throw an exception, but you never know. So it's always good to have this pattern, unlock in a finally block. Okay, so now if I were to run this thing, the behavior is going to be similar to what we saw with the synchronized keyword. All right, so this is locking on the instance of the counter itself, which was created. So it is going to be like what you saw, right? Whatever thread increments also decrements before any other thread gets in. And this also handles the multiple counter problem as well. So for example, if I were to have another counter here, which is counter 2, and then I'm going to, sorry, this is counter 2 here, and then I were to create another thread, which is second instance. Well, what happens when this runs? The runnable is called, and now the L on which it is locked is the L member variable of this second counter instance, which is counter 2. Okay, so this is not going to be blocked by any of these other threads. So this should happen independently and possibly interspersed with the other threads. Yeah, so you see here, the second instance is interspersed, but again, increment and decrement happens in order, and these threads increment and decrement happens in order and is not interspersed with any of the other stuff over here. So this is locks in Java.